This video is sponsored by Unacademy, one of the largest learning platforms in India. Check out their Learn Competitive Programming by CodeChef subscription and use our coupon code SimpleSnippets to avail discount. More on this later in the video. Hey, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And let's continue on with the binary search tree implementation that we've been doing since the last few tutorials in this DSA course, that is this DSA playlist. Now, as the title of the video suggests, in this video tutorial we are going to learn and understand how you can find the height of a binary tree. We are going to see the pseudocode and dry run the pseudocode onto our example, and also at the end of the video we are going to write a C++ program to implement this operation, that is finding the height of a tree. Now do note that if you've been following throughout this tutorials, in the last few tutorials, we're doing the implementation of a binary search tree. However, this pseudocode and this operation will also apply on a regular binary tree. That is because structurally binary tree and binary search tree are pretty much the same. So calculating the height of a binary tree and a binary search tree is pretty much exactly the same. Okay. So with that being said, let's get started. Now as you can see on the screen, this is our binary search tree and this is the root node. The name of the root node is N1. The address in the memory is #31. This is fictitious, this is fake. This is just for representation purpose. In the node we have the central value as the actual key or value or data, and the left and right are nothing but addresses to the left and right child nodes. Okay. So you can see N2 is created at #16 and #16 is the address stored as the left child for N1, and N3 is created at #99 address and #99 is stored as the right child of N1. So this is the overview. This is the pattern which is pretty much followed in the entire binary search tree. I'm guessing you guys already know this. You already have a hang of it if you've been following the entire tutorial series. If not, do check out the playlist. And talking about the height of the tree, again we've already discussed this, but just to give you a brief, the height of the binary tree is the number of edges or number of paths between the tree's root and its furthest leaf. So I hope you know what is edges. Edges is nothing but this path, this line which connects the different nodes, and we need to calculate the number of these edges between the root node, so this is the root, and its furthest leaf. So the leaf nodes are the end extremities after which we do not have any further nodes. So you can see these are the three leaf nodes, 1, 2 and 3. But we need to find out the furthest leaf. So you can see 1 and 2 are the furthest leaf because there are two edges in between. You can see 1 and 2, 1 and 2. And for this leaf node we only have one edge. So we will not consider this one. So according to this definition, the height of this particular tree is equal to 1 and 2. Correct? That is the number of edges between the root node and the furthest leaves. So just by looking at the definition, we can easily make out what is the height. But now when it comes to implementation, when it comes to applying this definition and logic and to write a program, we need to understand how we can calculate the height, right? So there has to be certain step-by-step process. So this is where the pseudocode comes into picture, and we are going to use the concept of recursion, that is recursive functions. We can also use the iterative approach, but that can be done in separate tutorial. In this tutorial we are going to discuss the recursive approach. So let's first understand the pseudocode and let's try to dry run it on our example and see how we can find the height of the tree. We've already found out that the height of this particular tree is 2. So if our pseudocode works fine, we should get this result as well. So let's talk about this pseudocode. So pseudocode is nothing but part English, part code kind of syntax, which can be easily converted to any general purpose programming language code. So it is something in between the two, and it is easy to convert a pseudocode into a program rather than plain simple English algorithmic steps. Okay. So this is the function name or the operation name, you can say height, which will give the height of the binary search tree or binary tree. Since it will return a numeric value, the return type is int, and it will accept an address of the node, hence tree node star. So tree node is nothing but this particular node class. This is what we've defined in our program in our C++ implementation side, and it will take an address. So it will take a pointer basically to this particular node. So we will obviously start with the traversal from the root node. So hence it is taking one node as the argument. Okay. So moving on. Before we start with the pseudocode, just to give you a brief about how you calculate the height, essentially what we will have to do is we will have to traverse from the root node and count the number of edges and reach the leaf node. But there is a catch over here, that is because for every node in a binary tree or in a binary search tree, we have two different ways which we can go. We can either go to the left or we can also go to the right. Correct? So we need to figure out which is the longer path, right? So that's why we need to traverse both left and right and count the number of edges by reaching the leaf nodes. And after counting, we need to compare the count, that is the left side count, that is the number of edges on the left, and we have to compare it with the number of edges on the right and determine which is the greater one, and that would be the height of the tree. Understanding this point? So I just tried to put out a brief of how you calculate the height. Of course, we will see the pseudocode, but in plain simple English terms, the way we calculate the height of the trees, we will of course have to traverse both the left and right sides of a tree, and we have to keep on counting the number of edges on the left as well as on the right, and whichever is the longest, we have to make a comparison at the end, and that would be the height of the tree. Correct? Alright. This video is brought to you by Unacademy. They have launched a competitive programming subscription with CodeChef, and this is an all-round solution for anyone and everyone who wants to be a pro in competitive programming space. Some of the special features include learning from the world's best programmers, ICPC World finalists and software engineers working in the best product companies, interactive sessions where you can engage with your expert educators, structured courses with doubt solving by expert panel of teaching assistants and community members, teaching in both English and Hindi language, so language is not a barrier, and I personally find this very cool. And in addition to this, there are special free live lectures that you can attend to experience the subscription. Oh, and did I mention you get an extra 10% discount with our coupon code Simple Snippets on your 6 and 12 month subscription, and get the first month course at flat 999 rupees with this coupon code. Go to the link in the video description and check out the competitive programming package. So now let's see the pseudocode. Let's go step by step. The first thing that you pass in the tree node when you call the first height function is going to be the root node. So let's see the first call. So the first call would look something like this. We will say int height and you will pass the root node n1. Okay. So this is nothing but a pointer to the root node. And now let's start with the dry running with the pseudocode. So starting off with step 1, we first check if r equals to null, then return -1. So this is where the exit condition is. And when I say exit condition, when you are dealing with recursive functions, you will have a base condition or exit condition, which means that there will be a time when the recursion has to stop when all your conditions are met, and that is the base condition or that is the exit condition. Otherwise your recursion will go infinitely and you will get an infinite kind of loop and your program will stop working. So the reason why we are saying if r equals to null is because when this r node will point to null value, and that will only happen at the leaf nodes, right? You can see at the edges, the left and right of a leaf node is blank, which means it doesn't have any value, which means programmatically it will have null values. So when you reach the end, that is when you reach the leaf nodes, that time the r will become null and then you can return -1. So why are we returning -1? You'll understand that when we dry run this pseudocode, and that's the best way to understand pretty much most of the data structures concepts. That is taking a pencil and paper and dry running all the pseudocodes, all the algorithms, all the programs, and understanding the different changes that happen at every step. So right now r is nothing but n1, correct? So r is n1, so r is not null. So the first step will not be executed, which means this if block will not be executed. We will go to the else block. Since if is not executed, you'll go in the else. In the else you have some multiple steps, starting off with first step. First step we say 2.1, we say L height, you can also say left height, because as I mentioned we will have to traverse both left and right side of a binary tree, and then you have to make the comparison. So first we start with the traversal of left side of the tree. So that's why we say L height is equal to, and this is where you can see we are giving a recursive call. We are calling the same function height, and in brackets we are passing r of left. Now r is currently n1, which means r is currently pointing to n1. When I say r of left, what is there to the left of n1? You can see to the left of n1 we have hash 16, which is the address of n2. So when I say r of left, I am passing n2. So now I am giving a recursive call, because you can see height is calling height itself. So that's a recursion. And when this happens, the first height call, the first function call will go in a pause state. So that's how recursion works. I hope you guys know what is recursion and recursive functions. If not, I have a separate tutorial on recursive functions. Do check it out. It is very important. I'll link it in the video description, or you can also see a card on the top right corner. But moving on, as I mentioned, the first height function call will get paused, and it will get paused at step number 2.1. So let's do the pause symbol over here, and it got paused at step number 2.1. So let's write 2.1. This is where the first function call, that is the height function, has paused, and it is given a recursive call to a second function call, and inside that, as I mentioned, we are passing n2. So first function gave a call to this second int height function, inside which we passed n2. This L height and R height are variables inside every function, which we will calculate. Right now we don't have any value over here. We are saying L height is equal to height of the left side. So when this entire function will be done executing, it will return some integer value, because you can see the height function or height operation has a return type, and that will be stored in this L height. But right now the second height function call has to execute completely to return back to the first int height. So that's why we have blank values over here as of now. Let's proceed with the execution, and let's start with the execution of second height call, because the first function call is paused. Okay, so now when the second int height function call starts executing, R is nothing but n2. We can see over here n2 is passed. Again we check if R equals to null. No, R is pointing to n2, so R is not null. So we go in the else. Again over here we say at step number 2.1, L height is equal to height of R of left. So one more function call or one more recursive call is given. So third function call is given from the second height function at step number 2.1. So again at step number 2.1, this second int height function goes in a pause state, and this time we are calling n4, because when you say height of R of left, R is currently n2. What is there to the left of n2? You can see #6. #6 is nothing but the address of n4. So we are passing n4. So n4 will be passed over here. The second function call will go in a pause state, and we are calling third function. And now we will start with the execution of this third int height call. So for the third int height call, we are passing n4. So R is nothing but n4. Again, first condition, if R equals to null. No, R is not null. R is pointing to n4. We go in the else. We say step number 2.1, L height equals to, again a recursive call. So fourth function call is given, and we say height is equal to R of left. R is currently pointing to n4, who's there to the left of n4. This time we have null. So now we will pass null, and you can see the fourth function call, inside that we are passing null. The third height call is getting paused at step number 2.1. So let's write 2.1 over here, and it is paused. And now we will start with the execution of this fourth function call. So when the fourth function is called, we are passing null. So R this time is going to be null. And when you go inside this function in the very first step, this if condition becomes true, because now we are saying if R equals to null, then return -1. So this time R is null, right? So this condition becomes true. We will execute 1.1 and we will say return -1. So now this fourth int height call will return back to its calling function with a -1 value, correct? You can see return -1, and this -1 will be stored in this L height. So why is that so? Remember, the third function, that is this third int height function call, was paused at step number 2.1. At step number 2.1, you can see we are saying L height equals to the height function call, which means that the L height variable will store some value which will be returned by this function. That is, which will be returned by the fourth int height call, and the fourth int height call we just said is returning -1. So -1 will be stored in this L height variable. Okay, so I hope you're understanding. Let me do a return sign or return arrow. It returned with -1, and -1 was stored in this L height variable of the third function call. Okay, alright. So now the third function call, which was paused at 2.1, will proceed its execution from step number 2.2. It will go in a resume state. So from 2.1 you proceed to 2.2, And at 2.2 you can see we are saying r height is equal to again a recursive call, but this time we have to traverse to the right side. And for the third height call, the r value is n4. What is there to the right of n4? We have nothing but null, correct? So a fifth function call is given, a recursive call, and you can see we are again passing null. So from third int height function call, we are giving a recursive call to fifth height function call. After doing that, the third int height function call will go in a pause state, this time at step number 2.2, correct? And now we will start with the execution of this fifth function call. Now when you start with the execution of this fifth function call, which we passed null inside, this r becomes null. When r becomes null, the first step itself gets true because r equals to null, and we will go inside this if block. We say then return -1. So now we will return from this fifth function call back to the calling function. And who called this fifth function call? You can see the arrow. It was called by this third int height call, and we will return with the value of -1. And where will this -1 be stored? It will be stored in r height. So -1 will be stored in r height because you can see the third function call was paused at 2.2, which is this step. Over here we have r height is equal to height, which is a function call. So this height is done its execution and it is returning with -1, which will be stored in this r height variable. Okay. And now again this third function call will resume its operation from step number 2.3. So moving on to step number 2.3, now we can make that comparison. So the comparison is between these two variables, the L height, which is representing the left height, and R height, which is representing the right height. So if left height is greater, so you can see the if block is checking at 2.3. If L height, that is the left height, is greater, then return left height +1. Else, if it is equal or not greater, that is if the right height is greater or both of them are equal, then return R height +1. Now in this case, you can see L height and R height, both of them are -1. So this step number 2.3 will not be executed because L height is not greater than R height. It is equal, but it is not greater. So in that case, the else block will be executed because if it is not greater, it will either be equal or less. So if it is equal or less, then the else block will be executed, and in that case, we are simply saying return R height +1. So R height we just said is -1. So -1 + 1 will give us 0, correct? So from this function, we are returning 0, and where are we returning it? To the calling function. Who called this third int height function call? It was given by the second int height function call, right? So we are returning 0, and that 0 will be returned to the L height. Why is that so? Because you can see the second height function call was paused at step number 2.1. For this second int height call, the step number 2.1 is this step, which is saying L height is equal to height. So when the third height function call is done its execution, it is returning 0, and that 0 is over here, which is stored in the L height at step number 2.1. This is where it was paused. So now this second function call will resume its operation from step number 2.2. Okay. So I hope you are understanding so far how the values are returned, and we are basically calculating the left height and right height at every recursion and then making a comparison, and depending upon which one is greater, we are returning that value, and if it is equal, we are simply returning right height +1. Okay. Now as I mentioned, this second function call will start its operation from step number 2.2. In the second function call, the R value is n2, so R is nothing but n2. So at step number 2.2, we are giving one more recursive call. You can see we are saying R height. So we are now calculating the right height, and we are saying R height equals to height, which is another function call, which is the sixth function call. And this time we are saying R of right. R, as I mentioned, is n2. What is there to the right of n2? You can see it is #26, which is the address of n5. So we are passing n5 over here, and we are giving a recursive call. You can see the sixth recursive call is being given from this second function call, and we are passing n5. So this second function call will now again go in a pause state at step number 2.2. So this time it is paused at step number 2.2, correct? Now let's begin with the execution of this sixth function call. So for the sixth function call, that is the sixth height function call, we are passing n phi. So r is nothing but n phi. We check r equals to null. No, r is not null because r is n phi. So in the else part, we go and we again say 2.1, which is L height equals to again a function call, and we are saying r of right. So r is n phi. You can see r is n phi. What is there to the left and right of n phi? Both of them are null, correct? So r of right is nothing but null. So sixth function call is giving a seventh function call, and this time we are passing null. So when that happens, the sixth function will go in a pause state, and it will go in a pause state at step number 2.1. So at 2.1 it is paused. When you begin the execution of seventh height function call, when you pass null in it, it will of course execute the step 1 and it will return -1, correct? So immediately you will come back to the calling function. Who called the seventh function call? It was the sixth function call, and you are returning -1, and this -1 will be stored in the L height, because in the sixth function call you can see at step number 2.1 L height is on the LHS, and on the RHS was this function call, and which returned with -1. So -1 was stored in L height. So we've calculated the left height. Similarly, since the sixth function call will now resume its operation from step number 2.2, you'll proceed over here in step number 2.2. Now you will say r of right, which is n phi is right, which is again null. So again you'll pass null. So eighth function call will be given from sixth function call. When you pass null in the eighth function call, the first step will be executed because r will be equal to null, so you'll quickly return with -1. So again you'll come back with -1, and this time the -1 will be stored in the r height because we paused at step number 2.2. So -1 will be stored in r height. And now for the sixth function call, which will resume from step number 2.3, again we will make a comparison. If L height is greater than r height, you can see over here L height and r height is -1, which is equal. So this if block will not be executed, the else block will be executed, and inside that we are saying return r height plus 1. R height is nothing but -1 plus 1 will be equal to 0. So now 0 will be returned to the calling function. Who called sixth function call, or who called the sixth int height function call? It was called by second function call, right? You can see the arrow, blue arrow. So you'll just follow back and it will be returned, and you're returning 0, and the 0 will now be stored in r height. Why? Because you can see the second function call was paused at step number 2.2. That is this step. So at this step you're saying r height equals to height. So now the 0 that will be stored will be returned and stored in the r height. Okay? Alright. So when this happens, the second function call will again resume its operation from step number 2.3. Correct? So 2.2 is done. So now we will resume operation from 2.3 for this second function call, and for this second function call r is nothing but n2. So let's execute step number 2.3. For this second function call, we are making a check if L height is greater than r height. In this second function call, we just calculated the left height as 0 and r height as 0, correct? Both of them are equal, so else will be executed. In the else part, we are saying return r height plus 1. R height we just said is 0. So 0 plus 1 will be equal to 1. So now 1 will be returned from this second function call to the calling function, which is the first function call. Correct? So you'll return back and you'll return with the value of 1. And this 1 will be stored where? It will be stored at step number 2.1 for the first function call. So for the first function call, step number 2.1 is this step, which is left height. So left height will be storing a value of 1, which will be returned from this second function call. Okay? So now what we just did is we simply calculated the height of the left hand side, and this is not the actual height. The actual height is 2, and you'll understand when this 2 will be calculated ultimately. But we are just done with the left hand side using the recursion. And now the first function call will resume its operation from step number 2.2. So for the first function call, what is the r value? R value is nothing but n1. We are resuming with 2.2, and we are saying r height equals to height. So again a function call is given, which is the 9th function call, but this time we are saying r of right. R, as I mentioned, is n1 for the first function. What is there to the right of n1? You can see #99, which is the address of n3. So you are passing n3 over here. And now the first function will give a recursive call to the 9th function call. You're passing n3. And then the first function will again go in a pause state, but this time it will be paused at step number 2.2. So I'll write 2.2 over here. And now we can begin with the execution of this 9th function call. So for the 9th function call, the node that we are passing is n3. So r is nothing but n3. Is it null? No. You'll directly jump to step 2, that is the else part. In the else part, you'll say 2.1. You're saying L height equals to height function and you're passing the left child. So for n3, because r is n3, do we have anything to the left or right? No. So now you're passing null. So one more function call is given, one more recursive call, and you're passing null. Correct? So 10th function call is given. When you pass null, we know that this function will return -1. So it will return -1 again. And this -1 will be stored in step number 2.1 as the left height for this 9th function call, because this is where you call the height. That is the 10th function call, correct? Now you proceed to step number 2.2. I'm going a little fast because I'm guessing you guys have understood the entire working now. So at again step number 2.2, we are saying r height equals to again a function call, which is the 11th function, and you're saying r of right. When r is n3, the right of n3 is nothing but null, so you're passing null. When you pass null, the 11th height function call will simply return back with -1. I know this is getting a little shabby and cluttered over here, but by now I'm guessing you guys have got the hang of the recursion progression. And again it will return with -1, so -1 will now be stored in r height. And now the 9th function will again resume its operation from step number 2.3. Over here we are making a check if L height is greater than r height. L height and r height are equal, which is -1. So the 2.3 will not be executed, we will move to 2.4. In that we are saying return r height plus 1. R height we just calculated is -1. -1 plus 1 is equal to 0. So 0 will be returned from 9th function call to the calling function, which is the first function call. So 0 will be returned and 0 will be stored as the r height in the first function call, because you can see the first function call was paused at step number 2.2. This is step number 2.2 where we are calculating r height. And when 0 is returned from the right hand side, it will be assigned as r height. So I'm going to write 0 over here. And now the first function call will resume its operation from step number 2.3 because it was paused at 2.2. Step number 2.3 for the first function call, which is the first int height function call, is if left height is greater than r height. So now you can see there is a difference between left height and right height. Both of them we just calculated. Left height is 1 and right height is 0. So left height is 1 and right height is 0. So this if condition now becomes true. So now you'll go inside this if condition and you'll say then return left height plus 1. So left height we just said is 1. So you'll say 1 plus 1, which is equal to 2. And this, my friends, will be returned to the main function. Now in C++, in the main function is where we will call this first call, right? So we will get back 2 as the output. And initially, as I mentioned, the height of this tree is also 2. Which means our pseudocode worked perfectly fine and we got the height as 2, which is basically our final answer. So height is equal to 2. Okay, so this was the pseudocode for finding the height of a binary tree or a binary search tree using recursive approach, using recursive functions. I did go a little bit faster because we've been doing recursive functions a lot and it follows a similar pattern. Just that in this case we are calculating the left height and right height and then we are making the comparison. If you're still confused, I highly recommend that you pause this video, take a pencil and paper and dry run this entire pseudocode step by step just like we did in the video, and I'm pretty sure you'll understand it very clearly. And now let's do the last part, which is converting this pseudocode into a C++ code and running the program and seeing the output. Okay, so as you can see on the screen, we are continuing with the implementation of binary search tree, and as I mentioned, the height function, that is the calculation of the height of a binary search tree and calculation of the height of a binary tree, is exactly same. So in our class BST, this is where we've been implementing all the other operations. So we'll scroll down at the bottom of the class, and over here I'm going to paste the code of the height calculation. On the right hand side, I'll also put the pseudocode. You can compare it with this code, and we're using C++ programming, so there will be a little bit of change in syntax because the pseudocode is not the proper syntax. You can see this is the step 1, this is the step 2. Inside that we have step number 2.1, 2.2, and then 2.3, 2.3.1, and 2.4. So I'm not explaining the code line by line over here because this is pretty much very basic to understand. If you've understood the pseudocode, we'll simply waste time. That's why I just copy pasted the code. I'm obviously going to be sharing this entire code with you guys, so you can check out the official website for this article. I'll drop the link of this article in the video description. You'll get some theory as well as the code for this. If the code is not yet available, it will be available soon. But yeah, now let's just save this and let's go in the main function. You can see we already have certain options in our menu driven program, but you can see the option for height of a tree is not available. That is because initially we did not plan on implementing this, but let's do that. Let's hit enter and let's add one more option number. So option 5 is going to be for the height of the tree. Option 6 is going to be for clear screen. So we also have to make that change in the switch case. So option 5 is where we do the height of the tree, and this case will now become 6, which will clear the command prompt. So inside this case 5, when the option number is 5, which is entered by the user, we will simply print tree height, and then we'll say height equals to obj.height, and you'll pass the root. So this obj is nothing but the object of class BST. You can see in the main function at the top, we are creating this object, and then we are using this object to call the height function, and we are passing obj.root. So root is nothing but a pointer of type tree node, which is there as a data member in the BST class. I've explained this entire program when we started off with the implementation. So if you followed the previous tutorials, this should be a piece of cake to understand. If not, you can check out this entire code. You should be able to understand it. So after the execution, you'll return with the height, which will directly be printed on the command prompt because the height function returns an integer type variable. So that would be directly printed off onto the command prompt instead of storing it in a variable. You can also do that, but that's the extra step. We simply want to print it on the command prompt, right? So let's save this. Let's go to execute, compile and run. This should work, I'm guessing. Okay, so our program ran successfully, which means there is no syntax error. Now let's first enter some values in the binary search tree, or directly let's just calculate the height of the tree and let's see what happens. We should get a -1 as the value, because when we have no node in the binary search tree, we should get return -1 condition true. So when I hit option 5 and hit enter, you can see tree height is equal to -1. So this is also true in reality. The height of a tree which does not have any node is -1. The height of a tree when you have only one node, which is the root node, is 0 because you don't have any edges to calculate. So that means our code is working fine. Now let's just insert some values. Let's just insert the same values that we have in our tree in our example that we did. So option 1 you can see over here is for insertion. We've already done with the insertion, the search operation and other operations also. So do check out this DSA playlist if you want to know how you can do the operations. So option number 1, hit enter. This is where we enter the value of the tree node to insert in the binary search tree. The first root node is 30. I'm gonna hit 30. Again, let's insert one more. It is 18. Let's insert one more. It is 45. Inserting one more. It is 10. And inserting one more. It is 25. Now to see the entire tree that we've just created in our command prompt, you can see we have option number 4, which is printing or traversal. When I hit option 4, this is where our tree is printed. You can see the tree is basically rotated anti-clockwise 90 degree, but that's just for representation purpose on a command prompt. So 30 is the root node, then 18 and 45 are its immediate children, left and right children. In the diagram also you can see. Then for 18 you have two children, 10 and 25. So 10 is the left child, 25 is the right child. Alright, so the insertion is done. Now we want to see the height of the tree. So the height of the tree should come as 2. So I've cleared the screen. Let's print the entire tree again and let's hit option number 5 for the height of the tree. When I hit option 5, you can see tree height which is equal to 2. So this means our code is working perfectly fine. If you have this entire code, what you can do is you can run it multiple times, add more values, increase the height, decrease the height, see if the code is working fine. It should definitely work fine. And we have successfully implemented the height operation of a binary tree or a binary search tree successfully. We dry ran the pseudocode, we understood the working by taking the visual diagrams, and we also completed the practical side by converting that pseudocode into a C++ program. Okay, so I hope you liked this video. I hope you understood the entire working of height function using the recursive search approach for a binary tree or a binary search tree. If you understood it, if you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends. Definitely subscribe, as there are many more tutorials on data structures coming up in this entire DSA course, and a lot more on our Simple Snippets channel for computer science and information technology oriented subjects and students. So I'm gonna wrap this video up over here. Thanks for watching. See you in the next one. Peace.